Okay, hello and welcome back everybody. So I'm calling this section the perspective shift to quantum mechanics and a two-state system. And I know I've really been trying to emphasize that there are relationships to quantum mechanics the entire semester, and I've described the slight modifications in notation that do exist between maybe the true mathematical linear algebra and the quantum mechanical representation of vectors. But I'm going to go through them all here as well, and we're going to finish out by analyzing and really solving a two-state system that deals with polarization of light. So the first half of this video is really modified from a lecture that was given by Noah Graham at Middlebury College. So maybe I'll just say this is modified from Noah Graham. He's a physicist. His lecture was called Quantum Mechanics is Linear Algebra. So if anything you see fascinates you, I would go over to his webpage and see some of the other stuff he's created. He's at Middlebury College, which in fact is where I will be teaching next year. So very soon I'll end up being there as well. I'm in the math department though. So if you see any similarities between what I'm discussing here and maybe what Noah Graham has done before, that's why. And basically I want to start out with a kind of a language dictionary or a translation dictionary where we have a slightly different language. Okay, so let's go through translations. Not even the mathematical translations, I mean literally language translations. So in linear algebra we have vectors, and in fact everything that we've been working with this semester are column vectors. So the column vectors, these are the ones that we've been seeing with entries in them, v1, v2, all the way to vn, and even in infinite dimensions you could probably have column vectors. And these, as I've been mentioning the entire semester, can be represented like a psi. These are your quantum states. But there is something stronger than that people don't normally talk about. It's in fact the normalized column vectors, which are quantum states. So we have the property that since they are normalized, the sum of the absolute value of each of the vi's squared has to be equal to 1. So really the normalized column vectors are the quantum states. And something we really didn't discuss, because it's not the world's most important thing in a lot of linear algebra courses, is that we actually have an ability to represent vectors as row vectors. So you could actually represent a vector as v1, v2, dot, 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 vn into a row surrounded by parentheses. And of course this is equal to the column vector transposed, right? We still have this idea of a transpose, but in fact it really should be thought of as the column vector Hermitian conjugate. So I really should probably put some complex conjugates over those. These are the row vectors, or often dual vectors, some people refer to these. They're also going to be normalized for the same reason. And these are actually notated in quantum mechanics in the other direction. So you'll notice that the angle bracket switches sides. And even stronger than that, we give this the name the ket of psi. We give this the name bra of psi. And so together this is called bra-ket notation, like bracket, play on words of bracket notation. I believe it's attributed to Dirac, Paul Dirac. So that's how we'll refer to quantum states in rows or column vectors. And this is called the dual state or dual quantum state. It's dual because it acts against the previous state. And it's almost actually to our advantage to notate the entries of column vectors using superscripts if you really want to be particularly fancy, because you can get away with some Einstein notation then as we get to our next section. In the next section, when we consider maybe one psi against another psi and we look at their inner product, we actually don't notate them using the mathematical inner product. We just put a stroke in the middle. This is the inner product. And we can think about it as, if we're thinking about a row vector against a column vector, we maybe have w1, w2, dot, 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 wn against the column vector v1, and I'll put some subscript or superscripts there, v2, dot, 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 vn. And this will be, well, you can use Einstein notation. The physicists put the conjugate on the left side instead of the right side, which is fine, but we can use Einstein notation. Let's go wk v to the k, or in other Einstein cases, w k v to the k. K goes from 1 to n. So these are all the same as our regular inner product, which I would have notated as w vector against v vector. Those are all going to be the same. And it's useful because you just put the bra right next to the ket, and you immediately recover an inner product on the two of them. Thankfully, most of the time our linear operators look the same. These still mostly look like matrices, except we'll give them a different name. We'll either say that they're L in quantum mechanics so that we can save ourselves some space from writing out a matrix. But yeah, these are still just equal to matrices. So M1, 1, 1, 2, dot, 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 M1, N, dot, 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 M, N, N, dot, 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 M, N, 2, M, N, 1, M2, 1, dot, 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 M2, 2, dot, 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 dot. Still matrices. So thankfully those kind of come along for the ride at the same time, except for maybe sometimes in quantum mechanics they like to put little hats on operators. So you may gain a hat just for fun in linear algebra. I do really love the quantum mechanical version of an eigenvector. An eigenvector is notated as lambda, and you just put a ket around it. Like, how natural is that? This is the vector corresponding to eigenvalue lambda. Like, how fantastic is that? In fact, it's the eigenvector, right? Eigenvector corresponding to eigenvalue lambda. Like, that's just the nicest thing. So you write it out like this: L hat against lambda is equal to lambda against the vector lambda. Like, that is such a more elegant way of notating these things. So that's really nice. And then we can compute something called the expected value, or the expectation of a state with respect to an operator. So this is often written as bracket operator bracket state, subscript state. This is going to be the inner product of one state, and then the operator comes in and then it acts on the same state. So these are going to be the same state here. But what is that in terms of linear algebra, right? This is just this inner product, v against L on v, which, shows up all the time in terms of like computing Hermitian or symmetric or orthogonal, etc. So that's called the expectation. So those are kind of like our original translations that we can work with. And then when we get to, if we want to ask questions about kind of setting up a two-state system to see how this works, let's go ahead and do that. And we're going to start by just talking about the polarization of light. So when we have light in the real world, which we often denote physically as a little squiggly line with an arrow, denoting that it's a wave that's propagating in a specific direction, so these are called photons. It's a photon of light. It has a polarization. It is associated to something called a polarization, which in some ways is a direction in which we can consider the wave oscillations, if I can spell oscillations, to be parallel to. Okay, so these oscillations, the way I've written it, it looks like they're parallel to the up and down of the two-dimensional screen that you're looking at. But you could also have oscillations that kind of go in and out of the screen. So this would be like an up-down polarization, and this would be like an in-out polarization. So let's say up-down polarization, and then an in-out polarization. And you can in fact have circular polarizations as well. So it could kind of oscillate like this. This would be circular, or basically anti-circular, where they would oscillate in the other direction. Which we would probably normally call clockwise or counterclockwise, instead of circular and anti-circular. Anyway, so you've got these notions of polarization, which are basically directions in which we can consider the wave oscillations to be parallel to. And there's a really interesting phenomenon which occurs when we analyze the polarization of light. So let's just assume we have one photon that has an up-down polarization. we can construct filters in the real world, and these are what exist in your sunglasses. When you say you have a polarizing sunglass, this is called a polarization filter. And here I've put it at 45 degrees to up-down. Well, my up-down polarized light is going to try to fit through here. And what will end up happening is some of it will fit through. Some light will go through, and some won't. This is why your polarizing sunglasses actually work, is they only allow some of the light through. In fact, if this is truly up-down, which we'll call like 0 degrees, and if this is at 45 degrees, you'll find out that exactly half. So instead of writing some light, it'll be a 50-50 chance that any given piece of light will go through. So let's suppose that we keep measuring and eventually one piece of light manages to go through. Now it's 45 degrees polarized. And if we put another filter that we'll say is horizontally polarized right after this will be 90 degrees to original, or horizontally polarized. Then the 45 degrees polarized light will again have a 50-50 chance will go through. And so something eventually makes its way through, and it's going to be really hard for me to notate a horizontal polarization. Think about it like that. It pops out, and it's horizontally polarized, also known as 90 degrees polarized. Okay, so let's suppose we shot 100 photons through this setup. What we're going to get is 50 of the photons in the first setting are going to choose to go through, because there's a 50-50 chance. We're going to have 100 that are vertically polarized. We're then going to go through the first case, and 50 of them are going to remain at 45 degrees polarized because of a 50-50 chance, right? And then we send them through the horizontal, and there's another 50-50 chance. So only half of the 50 remain, and we jump down to 25 photons that are horizontally polarized. So you start with 100 photons. You end with 25 photons, polarized 90 degrees away. You start with 100 polarized at 0 degrees. Now, what goes on quantum mechanically is that if we had instead chosen the setup where we start with our vertically polarized light at 0 degrees, and then we immediately give it a horizontal filter at 90 degrees, then the output, because we start vertical and we're testing against horizontal amounts, no photons survive. And so if we pass 100 through the setup, we start with 100, which are vertically polarized at 0 degrees, and we end at a 0 chance of making it through. We end at no photons, 0 photons. So what this says is that the experimental setup, right, because in some sense, we're just, maybe the number we care about is the final number on the far right. What's happening is the experimental setup is fundamentally changing the outcome. Fundamentally alters the outcome. This is really quantum mechanics in action, is that the experimental setup is also known as our measurement. is called the quantum mechanical measurement. It fundamentally alters the outcome of any given experiment. So it's kind of a strange thing to happen, because a lot of times we like to believe that physics is kind of occurring all by itself, independent of our influence on it. But we see in quantum mechanics that our influence is, in some ways, the physics. What we're able to measure, which is the polarization of light, what we're able to measure 100% depends on how we decide to measure it. Because suppose we just wanted to measure, horizontally polarized light, it just depends on if we put a 45-degree filter in the middle or not. And that's totally up to us to decide whether or not we're going to put it there. We're going to obtain a different answer in an experiment depending on how we set up the experiment. So what happens in quantum mechanics is we need to develop postulates which help us still make sense of the outcomes of experiments where our setups can fundamentally alter the measurements we receive. So we have something called quantum mechanical postulates. Tell us how to interpret and perhaps, set up experiments when the results of the experiments themselves depend on how we set the experiment up. So the first postulate it all goes back to linear algebra. So the first postulate, the current state is a normalized vector, which means it'll always be a normalized vector. And there are no quote-unquote hidden variables. So hidden variables are basically influences that are not able to be measured. We call this immeasurable influences. So everything that can describe the quantum system is assigned a measurement. The second postulate says that any physically measurable quantity is described by a Hermitian operator. We'll call it H hat here. The third postulate is that all possible results of the experiment, results meaning, numbers we see. Okay, so we perform an experiment, we get a number out of it. These are eigenvalues of H hat, our measurement. Postulate 4, since H is Hermitian, then any given state can be represented as a superposition of states against the eigenvectors of H, because the eigenvectors are necessarily orthonormal. So I is in some index set here. And the probability that we measure, so it's all about a probability that we measure a specific outcome. We measure the outcome lambda I given the state psi is the magnitude of lambda I against psi squared. And then the last postulate is kind of the one we were witnessing in polarization, is that after a measurement of, let's say, of lambda I, the state psi immediately becomes the state lambda I. So the original state, whatever it happened to be in, if you recover a specific measurement, it collapses. This is known as wave function collapse. So you no longer have alternate probabilities. You immediately recover exactly that eigenstate. Now let's see how these postulates behave with our polarization experiment. So let's just do a massive example of polarization. And in fact, we'll do polarization with Schrodinger's equation. So looking at the postulates, the current state is a normalized vector. Easy enough. We've got psi represents the polarization of light. Nothing more needs to be said. Any physically measurable quantity is described by a Hermitian operator. So what do we want to measure? We want to measure polarization. And in fact, which polarizations do we want to measure? We want to distinguish between up-down polarization and left-right polarization. This is where you can see we deal with abstract vectors. This is why I emphasize abstract vectors this entire semester. We don't really have them written as row or column vectors. It's just up-down versus left-right. And we want to construct a Hermitian operator which represents a measure. So we need a Hermitian operator H, which represents the up-down measurement. What we want out of this should give H on up-down equals itself, and H on left-right equals 0. So H up-down on up-down gives itself, H up-down on left-right gives 0. In fact, the 0 vector that I'll write like this. You can always have the 0 vector around if you want. But this gives us enough if we decide to represent psi in the basis, the orthonormal basis of our two states. So we define these to be an orthonormal basis, and then we can, as an orthonormal basis, and then we can decompose psi as really the sum of up-down against psi, multiplying up-down, plus left-right on psi, multiplying left-right. But going back to representing vectors, that means we can represent this as up-down against psi and left-right against psi in the basis up-down, left-right. And then also, these two tell me that you can represent H like a matrix where the entries are just up-down against H hat, up-down. Then you have up-down against H hat, left-right. You have left-right against H hat, up-down. These are all still H hat up-downs. And you have left-right against H hat, left-right. But we know what these values are. This is the inner product of up-down against up-down, but everything's an orthonormal basis here, so this has to be 1. The rest of them, because we're looking at inner products against other objects, against each other, we get 0 and 0, and because H hat sends left-right to 0, the 0 vector, this term also has to be 0. We end up that H up-down can be represented, right? This is why matrix representations are so important, is that H hat up-down can be represented in the basis up-down, left-right as the matrix 1, 0, 0, 1. And now we can really start to do some serious linear algebra. So to that end, we have a few other measurements we could take. If we wanted to go ahead and take the left-right measurement, we would see that this has a matrix representation given by 0, 0, 0, 1 in the specific basis up-down, left-right. We could also even do H of my 45 degrees, right? This is pretty important that we can construct the 45 degree measurement because we include it, and it gets included at 1/2, 1, 1, 1, 1. That's because the 45 degree measurement is mapping, it's giving that 1/2 characteristic to each of the other directions, right? So let's go ahead and see how what we're going to do is we're going to move and ask the question about the probability that we measure a specific outcome, in this case left-right, given a specific state that we start with. And we'll see how that shows up in our two-state system. So to compute let's say we start in the up-down state. Let's say this is psi, our current state, which is the case that we started with when we talked about polarization. We started in an up-down polarization. This has a representation 1, 0. There's two different scenarios, right? There's the scenario 1, where we have the photon 45 degrees 45-degree photon, and then horizontal. We have our horizontal photon. Or there's scenario 2, where we have vertical photon and then only the horizontal polarizer, and then we test about a horizontal photon. We have cases for each one of these. We can use matrices to describe this. What is the 45-degree matrix? It's this one. The 45-degree matrix is 1/2, 1, 1, 1, 1. What is the horizontal matrix? It's this one. Horizontal matrix is 0, 0, 0, 1. What is our initial state? 1, 0. And then what is our final state? We don't know. Now, unfortunately, because we like to write things from left to right when we read them, we perform mathematical operations in the other direction. So really what we should be computing is moving in the other direction, which looks like 0, 0, 0, 1, axon 1/2, 1, 1, 1, 1, axon 1, 0, our initial vector. And we'll go ahead and compute the matrix multiplication. So when I compute that matrix on that vector, I end up with 1/2 times 1, 1, because I get 1 plus 0, 1 plus 0. And then I bring my other vector down, 0, 0, 0, 1. And the output of all of these rows against that column gives me exactly 1/2 on 0, 1, or 0, 1/2. If I repeat this experiment in the latter case, where I'm still starting at the vector 1, 0, and now I'm only testing 0, 0, 0, 1 against it, then I have 0, 0, 0, 1, or 1, 0. Then all rows against all columns gives me the output 0, 0. I now ask the question, right? We can follow up with our final postulate, well, fourth postulate, I should say. I'm going to ask the question about the probability that I measure a specific outcome. So what is the probability? Or in other words, what is the percent of photons which are horizontally polarized? What I do is I look at my vector 0, 1/2, and I'm computing the expectation against the eigenvector that corresponds to left, right. So I'm going left, right against this vector, which is 0, 1/2, which is really 1/2 times the right, left polarization, and then I'm squaring this. This is just 1/2 squared, which is 1/4, which is 25%. 25% scrolling all the way back to my original polarization experiment is exactly what I ended up with in the first scenario. 25% of the photons made it through. In the second case, what is the percent of photons which are polarized? I can compute the same thing, but it's against the vector 0, right? So it's really not going to help me much. Exactly 0%, which also agrees with the experiment. So this is how we would translate those two experimental setups into quantum mechanics and linear algebra and compute our answer. But let's do the Schrodinger's equation on this. On this system and see what it gives us. So recall Schrodinger's equation, I h bar d dt on psi, and I'll write it as psi of t here, equals h hat on psi of t. And then there's always an initial condition if we're going to actually evolve something. And in this case, let's go ahead and choose the most exciting h hat, which is this 45 degrees h hat. We'll say it's 1/2, 1, 1, 1, 1. And let's choose our initial condition as what we did before, which is really the state 1, 0, as represented in the up, down, and left, right basis. That's Schrodinger's equation. And this is a first order, linear, homogeneous, constant coefficient ODE, which we know how to solve. So let's go ahead and rewrite it in terms of vectors so we can actually see how we learn to solve this. As vectors, let's just eliminate the h bar. That's not going to play a big deal for us, but that's an important constant. So we have I d dt on x as a vector. I'm going to replace psi with my vector, equals my matrix 1/2, 1, 1, 1, 1 on x as a vector. Or I can eliminate d dt and just write it as I times x prime, and my initial condition at time 0 is 1, 0. So let's go ahead and solve this and see what we get. Well, to solve this, the solution is given by x of t equals the matrix exponential. One thing I should do is divide by I, also known as multiplying by negative I. Matrix exponential e to the minus I t over 2, 1, 1, 1, 1, times the initial vector, 1, 0. So to compute the matrix exponential, we need to compute some matrix diagonalization. And so let's diagonalize negative I over 2, 1, 1, 1, 1. And in fact, we can get away with just diagonalizing 1, 1, 1, 1, and then bring negative I over 2 along for the ride. So let's diagonalize 1, 1, 1, 1. Let's find some eigenvectors, or eigenvalues first. And we're going to take the determinant of 1 minus lambda, 1, 1, and 1 minus lambda. This is going to give me 1 minus lambda squared minus 1, also known as lambda squared minus 2 lambda, and then I'm going to get a plus 1 minus 1. So this is equal to 0. I can factor out a lambda. I see that lambda is either 0 or lambda is 2. These are my two eigenvalues, which means that my eigenvectors come from 1, let's choose the lambda equals 0 case, 1 minus 0, 1, 1, 1, against x1, x2. This equals 0, 0. And if I read the first row, it says that x1 plus x2 is 0, or in other words, x1 is negative x2. That's telling me that x corresponding to lambda being 0 is the vector x1 and negative x1, or if I replace the x1s with 1, I get 1, negative 1. Corresponding to lambda equals 2, I have the matrix negative 1, 1, 1, negative 1, against x1, x2 equals 0, 0. This sends me to x1, well, negative x1 plus x2 equals 0, which is equivalently that x1 equals x2. So my eigenvector corresponding to 2 is equal to x1, x1, or if I replace each x1 with a 1, corresponds to 1, 1. Therefore, I can diagonalize as this matrix 1, 1, 1, 1 equals my two eigenvectors, 1, negative 1, and 1, 1, against the diagonal matrix 0, 0, 0, 2, and then the inverse of my vector, or my matrix on the left, which will be 1 divided by its determinant. The determinant is 1 minus negative 1, also known as 2. So I have a 1/2 here. Then I have 1, negative 1, 1, 1. So there's my diagonalization, which means I can compute the matrix exponential, e to the negative I over 2t on this matrix, by just applying it to the diagonal. And what I get is e to the 0, also known as 1, and then a 0, 0, and e to the negative I t. And then I have a 1/2, 1, negative 1, 1, 1. If I decide to actually compute this out, I can compute that first and that second. Computing on the left gives me all rows against all columns. I have 1, e to the minus it, negative 1, and e to the minus it, against 1/2, 1, negative 1, 1, 1. This is going to give me all rows against all columns. 1/2, looks like I have 1 plus e to the minus it, and then I have negative 1 plus e to the minus it. I have negative 1 plus e to the minus it, and I have 1 plus e to the minus it. I can distribute the 1/2 to the inside, and I end up with 1 plus e to the minus it over 2, negative 1 plus e to the minus it over 2, negative 1 plus e to the minus it over 2, and 1 plus e to the minus it over 2. So this is the matrix exponential, and we know our solution is the matrix exponential acting on the vector 1, 0, our initial vector. Multiply by 1, 0 to get solution to Schrodinger's equation. So when I multiply this by 1, 0, I'm just doing all rows against the columns, and I end up with my vector x evolving over time is the vector 1 minus e to the minus it over 2, and negative 1 plus e to the minus it over 2. And this, of course, is the quantum state of the system, and the quantum state of the system is written with respect to the up-down and the left-right basis. So the quantum state is the following superposition 1 minus e to the minus it over 2 against the up-down state plus -1 plus e to the minus it over 2 against the left-right state. If I go ahead and plot this outcome, so let's plot psi of t, and in fact, because there are some imaginary terms here, the best I can do is plot the real part of psi of t with two particular colors. We're going to do this color on the left-right term, and we're going to do this color on the up-down term, the up-down components. What we will see is an oscillation between eigenstates. If you look, this is where we start. This is where we start at all up-down component. And as that amount decays, we start to gain some left-right. You gain left-right components. And notice that this is below the x-axis. That's because it's the magnitude squared is the probability, so you would square it and it would become positive until you're down here and you have all left-right component. And then you start to lose the left-right and you regain up-down component. And it just oscillates the whole time between all of your eigenstates. And this is really where we see the wave-like nature of quantum mechanics show up, is the solutions to Schrodinger equation are waves. You will always recover waves like this, where you oscillate between possible eigenstates. Anyway, that's where we're going to stop today. I know it's been quite a long video. Lots of really cool stuff. Unfortunately, I'm not a physicist, so if you're really interested in this, go ahead and find your favorite physicist, ask them more questions, but I can probably answer a little bit if you ask. Anyway, I'll see you in the next one. We'll tackle one more problem, and then we're done for the semester. I'll see you then. Bye.